Chapter 8, General Linear Transformations, Section 8.1, General Linear Transformations. If T from V to W is a mapping from a vector space V to a vector space W, then T is called a linear transformation from V to W if the following two properties hold for all vectors U and V in V and for all scalars K. T of Ku has to equal K times Tu, so you need to be able to pull out constants. And Tu plus V has to be Tu plus Tv, so you have to be able to separate addition. In the special case where V equals W, the linear transformation T is called a linear operator on the vector space V. For our first theorem, if T from V to W is linear transformation, then T of 0 is 0. So linear transformations send the 0 vector to 0, and T of U minus V is T of U minus T of V. So that should follow straight from Tu plus V. But anyhow, we can prove this real quick. Let's look at T of 0. Then T of 0 is 0 times an arbitrary vector U. And then we can pull out 0 by this homogeneity property, that first property. And we'll get 0 times Tu, but then that'll just be 0, because Tu is a vector also. We can prove part B by writing Tu minus V as addition, where instead of subtracting V, we just add minus 1 times V, and then all we have to do is separate it out into Tu plus minus 1 times T of V, but that's the same thing as Tu minus Tv. As an example, how about we verify that every matrix transformation TA from Rn to Rm is also a linear transformation? Well, remember that we have homogeneity and additivity for matrix transformations. So that implies that TA is a linear transformation. By homogeneity, I just mean that when you have a constant times a matrix, you can insert the constant into the matrix, just multiply all the entries. And additivity, same thing. We can separate matrices by just adding their components. Let's look at example 2. Let V and W be any two vector spaces. Let's verify that the mapping T from V to W such that T of V is equal to 0 for every V is a linear transformation called the 0 transformation. So this is the transformation, just takes any vector, makes it into 0. So let's look at T of U plus V. So that's equal to the 0 vector. Remember, T of U is also equal to the 0 vector. T of V is equal to the 0 vector. T of K times U is equal to the 0 vector. So that means that if we have T of U plus V, then that is definitely equal to T of U plus T of V, because it's just saying 0 is equal to 0 plus 0. Also, T of Ku would have to be equal to K times T of U, because that's just saying that that 0 is equal to K times 0. Let's let V be any vector space and verify that the mapping I from V to V such that I of V is equal to V is a linear transformation called the identity operator. So let's look at I of U plus V. Well, that would just be U plus V. The identity operator just leaves you with the vector you started with. Let's look at I of U. So that would be U. I of V is just V. I of Ku is just K times U. And that means that I of U plus V is just I of U plus I of V. Because I of U plus V is U plus V, I of U is U, I of V is V, so it's just saying U plus V is U plus V. And as for I of ku, well, that'll definitely be k times I of u, because I of ku is ku, and k times I of u is k times u. If V is a vector space and C is any scalar, then let's verify that the mapping T from V to V given by T of x equals C times x is a linear operator on V. If C is between 0 and 1, then T is called the contraction of V with factor C, and if C is greater than 1 is called the dilation of V with factor C. So let's look at T of ku. So that's just C times ku by the definition we got. But C and K are both scalars, so we can just swap their orders. So that'll be K times Cu. But Cu is T of u. So this is just K times Tu. How about T of u plus V? Well, that would be C times u plus V. And we can distribute over vectors, so that'll be Cu plus Cv. And Cu is Tu, and Cv is Tv. So that works out too. How about we let P of x equal just a polynomial, C0, C1x, etc. through Cn, xn. So it's a polynomial Pn, and let's define the transformation T from Pn to Pn plus 1 by the transformation that just takes x and multiplies it by the polynomial. So T of a polynomial just throws x onto each of the terms. So the constant term gets an x, the x term becomes x squared, and so on. Let's verify that T is linear. Okay, let's look at T of Kp. So we have to just verify that we can pull out constants. So let's see, T of Kp in this case is T of k times the polynomial P of x. So that's just x times Kp of x. So that's k times x, P of x. I can just switch the order. So that's k times Tp. Okay, beautiful. Let's look at it for two different vectors. How about P1 and P2? Let's see if we can separate addition. So T of P1 of x plus P2 of x. So that would be x times some polynomial P1 of x plus another polynomial P2 of x. And we can distribute the x. So that'll be x times P1 of x plus x times P2 of x. And that'll be, well, xp1 of x is just t applied to P1, and xp2 of x is just t applied to P2. Perfect, so t is linear. How about we let V0 or V0 be any fixed vector in a real inner product space V, and let's let T V to R be the transformation T of x equals x V0, the inner product. So it maps x, a vector x, to its inner product with V0. Let's verify this transformation is linear. Okay, so let's check T of ku. In this case, that's the inner product of ku with the vector V0, whatever it is. So that's k times u V0, because remember, when we have a constant times one of the parts of the inner product, we can pull it out. One of the vectors in the inner product, we can pull it out. So that's equal to k times tu. Okay, how about T of u plus V? So that'll be u plus V, inner product with V0. V0 is not equal to V, okay, so that separates into inner product of u with V0 plus the inner product of V with V0. And that's just T applied to u plus T applied to V. Cool, so that's a linear transformation too. Let's look at M and N, the vector space of n by n matrices. And each part will determine whether the transformation is linear. So first, let's look at T1 of A equal to A transpose. How about T1 of Ka then? So that would be Ka transpose, or, sorry, Ka transpose. I should put the transpose outside because the matrix in this case is Ka. So now I can write that as K times A transpose, because transposing the constant's not going to do anything. I could just pull the constant out of this matrix over here. So it becomes K times A transpose, and that's just K times T1 of A. Okay, how about T1 of A plus B? Well, that'll be A plus B transpose for, two arbitrary matrices A plus B. So that's A transpose plus B transpose, and that's just T1 of A plus T1 of B. Because remember, transposing a sum, it's easy, it just goes right over. A little bit different for products, but that's okay. So these two facts imply that T1 is linear. How about T2 of A is equal to the determinant? Well, let's look at T2 of Ka. That'll be the determinant of Ka. Remember, when we pull constants out of determinants, they get raised to the power that is n. So it becomes K to the n times the determinant of A for an n by n matrix. Okay, so then that's K to the n times T2 of A, which is not K times T2 of A. So this implies that T2 is not linear for any n greater than 1. Obviously, for 1 by 1 matrices, it still works because you still just get K to the first power. But in general, K will be raised to some power that's greater than 1, so you won't be able to just pull out the K. So not linear. Also, if you looked at the determinant of a sum, determinant of a sum is not generally the sum of the determinants, so it fails in both respects for being a linear transformation. If x0 is a fixed non-zero vector in a real honored product space V, let's determine whether the transformation T of x equals x plus x0 is linear. Well, what if we looked at T of 0? T of 0 would be 0 plus x0, right? If I plugged in 0 for x, x0 is a fixed vector, so it doesn't change when I plug in 0. So T of 0 would be x0. And x0 is non-zero, so T of 0 is not equal to 0 in this transformation. So the transformation must not be linear, because T of 0 has to be 0 for linear transformations, as we've seen. You can also see this via a picture. If you were to look at, say, the 0 vector, and you look at, so let's say here's 0, and I'll put in some vector x, and let's say over here is some vector x0, then the vector x plus x0 ends up being this vector over here by the parallelogram rule. So notice what this transformation is doing. It's taking some vector x and it's translating it up along this x0 path so that you end up over here somewhere. So if I have a vector over here, it'll get translated up over there, right? Because this is the new vector x plus x0. So 0 ends up moving, translated up away from 0. 0 needs to end up exactly where it started with in order for a transformation to be linear. let's let V be a subspace of f minus infinity infinity, and let x1 through xn be a sequence of distinct real numbers, and let t from v to rn be the transformation t of f equal to f of x1, f of x2, through f of xn that associates with f the n-tuple of function values at x1 through xn. So we call this the evaluation transformation on v at x1 through xn, because we're basically just plugging in x1 through xn into f, and we're putting them all together in some sort of n-tuple. Let's verify that this evaluation transformation actually is linear. So first, let me give you an example just of what's happening here. How about if I had, let's say, x1 equal to -1, x2 equal to 2, and x3 equal to 4. So these are just three different values I want to plug in or evaluate. So I'm going to evaluate f of x equals, let's say, x squared minus 1. So just some function here. And I'll plug in each of those values. So t of f would be the tuple f of x1, f of x2, f of x3. So it's a 3-tuple in this case, order triple. So plugging in -1 squared minus 1, we get 0. Plug in 2 squared minus 1, we get 3. And 4 squared minus 1, we get 15. So it becomes 0, 3, 15 in the output of this transformation. Okay, now that we understand what it's doing, how about in general we look at t of kf. So that would be kf evaluated at x1 for the first component, and then kf evaluated at x2 for the second, and so on for however many things I want to plug in, however much I want to evaluate this thing, all the way up to xn. So then that's the same thing, because remember, multiplying some function by a constant, the evaluation is literally just taking the constant times that function at whatever you're evaluating it at. So that's just k times f of x1, k times f of x2, and so on. K f of xn. Okay, but that means that we can just pull out constants, because constant times a tuple, it just inserts into each component. So this is literally just k times f of x1, f of x2 through f of xn, which is k times t of f. So now we just have to check additivity. Let's do t of f plus g. So that would be f plus g evaluated at x1, f plus g evaluated at x2, all the way through, f plus g evaluated at xn. And that's equal to f of x1 plus g of x1, by definition of function addition. So then I have f of x2 plus g of x2 all the way through, f of xn plus g of xn. And we can separate out addition for tuples, right? I could just take this thing, add it to, well, I'll just take all of these first components out and add them to all of the first components, or the second component separately. So I'll take all of the f's, f of x1, f of x2, oh wait, I don't need that second parentheses, that should be an f. Okay, f of x1, f of x2, all the way through f of xn, and I will add that to g of x1, g of x2, through g of xn. So that's equal to t f plus t g. Perfect. let T from V to W be a linear transformation where V is finite dimensional. If S equals V1 through Vn is a basis for V, then the image of any vector in V, or any vector V in V, can be expressed as C1 times V1 plus C2 times V2 plus so on through Cn times Vn. So what we're saying is that C1 through Cn are the coefficients required to express V as a linear combination of the vectors in the basis S. So because these V1 through Vn are a basis for V, you can express V as some linear combination of these V's, and that means that the transformation of V can also be expressed as a linear combination of the transformations of those vectors. So that's pretty cool. How about we consider the basis S for R3, where V1, V2, and V3 are given right over here, and let's let T from R3 to R2 be the linear transformation for which T of V1, so it takes a three-dimensional vector and gives you a two-dimensional vector. T of V1 is 1, 0, T of V2 is 2, minus 1, T of V3 is 4, 3. Let's find a formula for T of x1, x2, x3, and then use that formula to compute T of 2 minus 3, 5. Okay, let's see. So we have x1, x2, x3 is equal to some constant C1 times 1, 1, 1, plus some other constant C2 times 1, 1, 0, plus some other constant C3 times 1, 0, 0. It has to be, right? Because by the previous formula, we have to be able to, well, by the previous formula, we'll look at the transformation, but even before then, x1, x2, x3 is just some vector. So it has to be able to be expressed as some linear combination of the basis vectors, otherwise this wouldn't be a basis, right? Okay, so let's see if we can figure out the C's, and then we'll use those to find a formula for the T based on the previous theorem. So by just taking equalities here, we have x1 is equal to C1 times 1 plus C2 times 1 plus C3 times 1, right? We're just adding up the first components. They have to be equal. So I have C1 plus C2 plus C3 has to be equal to x1. Okay, how about for x2? Let's see. We have C1 times 1, we have C2 times 1, C3 times 0, so there's no C3 for x2. So I just have C1 plus C2 plus 0 C3 is x2. Looking at x3, it's even better. We have a 0 for C2, we have a 0 for C3, so only the 1 for C1 will give us x3. So we have C1 is equal to x3. Okay, so I have C1 equal to x3. That's easy. I have C2 equal to, well, I'll take x2 and I'll subtract C1. So C2 is x2 minus C1, but C1 is x3. So C2 is x2 minus x3. And as for C3, well, that is x1 minus C1 plus C2, but that's x2. So that's just x1 minus x2. So let's rewrite this. I have x1, x2, x3 is equal to, instead of C1, I'll put in x3 times 1, 1, 1. And instead of C2, I'll put in x2 minus x3 times 1, 1, 0. And instead of C3, I'll put in x1 minus x2 and multiply that by 1, 0, 0. So this is the same thing as saying x3 times v1. I'm going back to the v notation just to be able to write out the transformation a little more simply. So this is x3 times v1 plus x2 minus x3 times v2 plus x1 minus x2 times v3. So first I wrote out what v1, v2, and v3 were, and now I'm working backwards and going back to just the letter representation to simplify things a little bit, because now I'm going to take t of x1, x2, x3, and set that equal to x3 times t of v1 plus x2 minus x3 times t of v2 plus x1 minus x2 times t of v3, because this previous theorem said that those coefficients c1, c2 through cn are the same ones that are required to express v as a linear combination. So I expressed this v as a linear combination with these coefficients, and now I'm using the exact same coefficients, and I'm just transforming the vectors on both sides. So now I can write it out as x3 times t of v1, which they told me is 1, 0, plus x2 minus x3 times t of v2, which they said was 2 minus 1. And then I've got x1 minus x2 times t of v3, which is 4, 3. Cool. So let's multiply out the x's. We get 4x1 minus 2x2 minus x3 for the first component, right? Because I'm going to end up with x3 times 1, and I'll end up with 2x2 minus 2x3, so that's where my minus x3 comes in, but then 4x1 minus 4x2, so the minus 4x2 and the positive 2x2 cancel, give me minus 2x2. And, oops, that was just for the first component. I still need 3x1 minus 4x2 plus x3 for the second component by multiplying those out, right? I get 0x3 from that, but I get minus 1 times minus x3 is plus x3, so there's my plus x3, and I end up with 3x1 and minus 3x2, and remember we had a minus x2 from over there, so I have minus 4x2. Okay, so then let's apply this transformation to 2 minus 3, 5. So 2 minus 3, 5. If we take t and apply that to it, we just plug in for x1, we'll plug in 2, and then for x2, we'll plug in minus 3, and then for x3, we'll plug in 5, and we'll get 9, 23. Let's let v equal c1 minus infinity infinity be the vector space of functions with continuous first derivatives on minus infinity to infinity, and let w equals f minus infinity infinity be the vector space of all real valued functions defined on minus infinity infinity. Let's let d from v to w be the transformation that maps a function into its derivative. That is, d of f is f prime of x. Let's verify that d is a linear transformation. Let's start with d of f plus g for two functions f and g. So that'll just be f of x plus g of x prime, right? We'll just take the derivative of f of x plus g of x, but derivatives are linear, right? We can take the derivative of some as the sum of the derivatives, so that's just f prime of x plus g prime of x. So that is just d of f plus d of g. I guess I shouldn't have said linear. The derivatives are additive. I mean, they are linear, but still, in this particular case, additive. Maybe not additive either. D of kf now. That's just k f of x prime. Derivative of k f of x, so that's just k times f prime of x. Remember, we can pull constants out of derivatives. So that's just k times df, or d of f. Wonderful. So derivatives are linear transformations. How about we let v equals c minus infinity infinity be the vector space of continuous functions on the interval minus infinity infinity. Let w equals c1 minus infinity infinity be the vector space of functions with continuous first derivatives, and let j from v to w be the transformation that maps a function f into its integral. So jf is the integral of f of t dt from 0 to x. Let's verify that j is a linear transformation. So first, let's just see what this is doing. How about an example function, f of x equals x squared? So in this case, j of f is the integral from 0 to x of t squared dt. So that's just t cubed over 3 evaluated from 0 to x, which is just x cubed over 3. So let's take a look at j of kf now. Well, that'll be the integral from 0 to x of kf of t dt. We could pull out the k because of the homogeneity of integrals, so that'll be k times 0 to x f of t dt. And this integral right over here is just jf, right? So it's just k times jf. Okay, well, let's do j of f plus g. Well, that'll be the integral from 0 to x of f of t plus g of t dt. And remember, integrals are additive, so 0 to x f of t dt splits off and adds to the integral from 0 to x of g of t dt, which is just j of f plus j of g. Wonderful. If t from v to w is a linear transformation, then the set of vectors in v that maps into 0 is called the kernel of t, and is denoted ker t. So ker t is all of the vectors that when you take the transformation and you apply it to them, you end up with 0. The set of all vectors in w that are images under t of at least one vector in v is called the range of t, and is denoted by r of t. So that's all the vectors that you can get out of the transformation. If ta from Rn to Rm is multiplication by the m by n matrix A, then what are the kernel and range of ta? Well, let's get the kernel first. So the kernel of ta, so it's multiplication by the m by n matrix, so the kernel is everything that gets sent to 0. So that's just the null space of A. The range of ta is everything that you can get out of that transformation. It's multiplication by the matrix, so that's just the column space of A. Let's let t from v to w be the 0 transformation. What are the kernel and range of t? Well, in the 0 transformation, everything gets sent to 0. So every single vector in v gets sent to 0. So it's all of v. What about the range? The range r of t is, well, the only vector you could possibly get is the 0 vector. So the range is just the 0 vector. So what is a set of 0? Let's let I from v to v be the identity operator. What are the kernel and range of I? Okay, so the kernel is everything that gets sent to 0, but the identity only sends vectors to themselves. So the only vector getting sent to 0 is the 0 vector. How about the range? Well, the range of the identity operator is everything that could possibly occur from being sent by something, right? Well, identity sends all of v to all of v. So the range is all of v. Let's let t from R3 to R3 be the orthogonal projection onto the xy plane. What are the kernel and range of t? All right, let's see if we can draw this. So we have in R3 the x, y, and z axes, and we have some point, let's say on the z-axis, let's say 0, 0, z. If we project downwards using our transformation t, then it projects onto the xy plane, so the z gets dropped and just becomes 0. So everything that gets sent to the 0 vector is any possible point on that z-axis. Anything over here will just have the z dropped and become 0 when we project downwards into the xy plane. So the kernel of t is just every single point in the z-axis. It's just the z-axis. All right, how about the range? Well, the range maybe is even more obvious. If I draw x, y, and z, then let's say I have some arbitrary point floating with coordinates x, y, z. It gets projected downward to a point in the xy plane via t. That point will just be x, y, 0. It just drops the z. So these are all of the possible points that could happen, right? We just project downward. Maybe I'll draw it with something like this. So this is the range. It's just the xy plane. That's everything you can get. It all gets projected downward. Let's let t from R2 to R2 be the linear operator that rotates each vector in the xy plane through some angle theta. What are the kernel and range of t? All right, well, here's the xy plane. And let's draw some vector v. So here's v. And I need to rotate it and get some other vector, tv. So I'll rotate this by an angle theta, and this will be the new vector I obtain, tv. So it goes from here to here like this. So the kernel is everything that gets sent to the 0 vector. Well, that would just be the 0 vector, right? Because any other vector that rotates is going to be sent somewhere else around. It won't be the 0 vector. Only the 0 vector rotating won't change it. So the kernel is just the 0 vector. Okay, what about the range? Well, by rotating one vector by some theta, I could get to anywhere else I wanted to in all of R2, right? If I wanted to get to a different one, I would just rotate a different vector. So the range is all of R2. I can get everywhere. Let's let v equals c1 from minus infinity to infinity be the vector space of functions with continuous first derivatives on minus infinity to infinity. Let w equal f minus infinity to infinity be the vector space of all real valued functions defined on minus infinity to infinity. And let d from v to w be the differentiation transformation df equals f prime of x. What's the kernel of d? Well, the kernel of d is everything d sends to 0, so that's all of the functions f of x such that the derivative f prime of x is equal to 0. Well, we know what functions have derivative 0. That's the set of constant functions, right? And derivative of any constant is 0. So the constant functions, or the set of constant functions on the interval minus infinity to infinity, the real line, that is everything the derivative sends to 0, so that's the kernel of d. If t from v to w is a linear transformation, then the kernel of t is a subspace of v, and the range of t is a subspace of w. How about we prove this? To show that the kernel is a subspace, we must show that it contains at least one vector and is closed under addition and scalar multiplication. By part A of theorem 8.1.1, the vector 0 is in the kernel, so the kernel contains at least one vector. Let's let v1 and v2 be vectors in kernel of t, and let k be any scalar, then t of v1 plus v2, remember it's a linear transformation, so that's t of v1 plus t of v2, that would just be 0 plus 0, because they're in the kernel, right? The kernel sends any vector v1 and v2 inside of it to 0, so that's just 0. So that means that v1 plus v2 is also in the kernel. If we have t of k of v1, then we can just pull out the k and get k times t of v1, so that would be k times 0, which is 0, so k v1 is also in the kernel. All right, so that shows the kernel is a subspace. How about the range? To show that the range is a subspace, we must show that it contains at least one vector and is closed under addition, scalar multiplication. However, it contains at least the 0 vector of w, since t of 0 has to be 0. Let's prove now that it's closed under addition and scalar multiplication. We must show that if w1 and w2 are vectors in the range, and if k is any scalar, then there exist vectors a and b for which t of a is w1 plus w2, and t of b is kw1. But w1 and w2 are in the range. So that means that there must be vectors v1 and v2 in v, such that t of v1 is w1 and t of v2 is w2. We have to be able to get to w1 and w2 from vectors in v if they're in the range. That's the definition of range. So the following computations complete the proof by showing that the vectors a equals v1 plus v2 and b equals kv1 satisfy the desired equations. Let's look at t of a. Well, that would be t of v1 plus v2, which is t of v1 plus t of v2, so that's w1 plus w2. So the vector a equal to v1 plus v2 is what gives us w1 plus w2, so that means w1 plus w2 is in the range. The sum of vectors is in the range is in the range. How about t of b? Well, that would be t of kv1, and again we can pull out the constant, so that's k times t of v1, which must be k of w1. So this means that k of w1 must be in the range because it comes from b, which is in v. Differential equations of the form y double prime plus omega squared y equals 0, where omega is a positive constant, arise in the study of vibrations. Let's confirm that y1 equals cosine omega x and y2 equals sine omega x are solutions of these differential equations, and let's use them to find a general solution. So instead of y double prime, how about I plug in cosine omega x? So I'll plug in cosine omega x double prime and add that to omega squared times cosine omega x, and I want to know that that equals 0. So let's see. So that's the same thing as, I'll take the first derivative and I'll get minus omega sine omega x prime, because when I take the first derivative of cosine I get minus sine, and I have to use the chain rule and make the constant hop out in front, and then I'll add that to omega squared times cosine omega x. I don't have to take any derivatives here, I have no primes. There's no prime over there. And I'll take one more derivative, so derivative of sine will be cosine. I'll have to hop out that omega again because the constant, so I'll get minus omega squared cosine omega x plus omega squared cosine omega x. Oh, that's beautiful, it's 0. They cancel each other out. Okay, now let's check the other one, y2. So that'll be sine omega x double prime plus omega squared sine omega x, and that's equal to omega cosine x, omega cosine omega x, sorry, prime, because I'm taking the derivative of sine, and that's cosine, and the omega hops out again by the chain rule, so plus omega squared sine omega x. Okay, and that equals minus omega squared sine omega x plus omega squared sine omega x, and again that cancels and gives you 0. It's handy that the derivative of cosine is minus sine. Okay, so let's find a general solution now. So we have D from C2 minus infinity to infinity to C minus infinity to infinity, where d of y is equal to y double prime plus omega squared y. And we won't prove it, but it turns out that the dimension of the kernel of D is actually equal to 2. This is proven in textbooks on differential equations. Maybe you could take my word for it. Otherwise, feel free to research if you don't. But in any case, the fact that the dimension of the kernel is 2 is very helpful for us because we just showed that y1 and y2 are solutions of these differential equations. So that means that any linear combination of these two guys would have to be the general solution because these guys are linearly independent. They're two linearly independent vectors. The dimension of the kernel is 2. That's what's getting sent to 0. So this means that we could write a general solution y equal to c1 cosine omega x plus c2 sine omega x. And that'll be a general solution. Let t from v to w be a linear transformation. If the range of t is finite dimensional, then its dimension is called the rank of t. If the kernel of t is finite dimensional, then its dimension is called the nullity of t. So the range, provided it's finite dimensional, has its dimension called the rank. The dimension of the kernel, if it's finite dimensional, is the nullity. We denote the rank by rank of t and nullity by nullity of t, or null t. The dimension theorem for linear transformations says that if t from v to w is a linear transformation from a finite dimensional vector space v to a vector space w, then the range of t is also finite dimensional, and the rank of t plus the nullity of t is the dimension of v, the original vector space.